He's a member of the Technology Integration Group, team leader for File and Storage Systems Task Group. He's also a member of the Program Committee and, has saved us on numerous occasions. Sarp Oral.
Good morning, everyone. First, this is a continuation of what we have been doing for the last 3 years. So think this presentation as an update from last year's. There are some new things, but there are some old things as well. And I'm just the spokesperson for the effort. Before I start, the nice folks from Oak Ridge, would you please rise up? Dave, Jason, Dustin, Blake, thank you. James over here. Galen and Sudarshan, are you in? Nope. Okay. These are the guys who actually did the work. I'm just puppeteer talking about it. Dave Vazel, are you here? Okay. Would you please rise up? He is also our grant worker. Thank you. So this talk is about our next generation spider file system. And your PowerPoint has died.
I'm sorry?
Your PowerPoint has died. Oh, here you go. Okay. So I'll try to wrap this up quickly. This talk will be about Spider 2, our next generation Spider file system. So I'll start with our first original Spider file system and give you an update on what we have done up to date on that one and continue with Spider 2. So we deployed Spider in 2008. At the time, it was the fastest raster file system in the world. We designed it to perform at 240 gigabytes per second. We had 4 MDSs, 192 OSSs, 1344 OSTs. It was a center-wide shared resource at the OLCF, serving all of our supercomputers and computing clusters, and etc. Jaguar was the main consumer. It had more than 18,000 clients. It was a 2 petaflops machine with 300 terabytes main memory. So we finished deploying Spider in 2008. We commissioned it. We rolled it into production. And right after that, we said, OK, let's start working on Spider 2, the next Spider project. And Galen just came in. So I got everybody rise up from OLCF because this is the continuation of the work. We missed you. So there's Galen. OK. Galen was instrumental up until he switched roles at OLCF for this Spider 2 project as well. So what were the motivations for Spider? We wanted to create a single shared storage pool for all OLCF resources. We wanted to provide aggregate performance and scalability for all OLCF resources at the lab. We wanted something that's resilient against the system failures. So when a machine goes down, your data won't go down with the machine. It should be accessible through other means at the center. And we wanted to allow growth of the storage pool by adding on later on to it without disrupting the services. So the original Spider met all of these design requirements, and when it came designing Spider 2, we found out that these design motivations were still valid. So what happened since then? We upgraded Jaguar. The new machine is called Titan. Some of you might have heard about it. It's still in the acceptance. It's a nice machine with, again, 18,688 nodes. It's a 27 petaflops machine. It has 18688 NVIDIA Kepler GPUs in it. The interesting part for us here is it's doubled in scalar system memory. It's now 600 terabytes. the total system memory size is 710 terabytes, including the GPUs. So what happens when you upgrade from a 300 terabyte machine to much more powerful 710 terabytes machine? Your I/O demands increase. Therefore, we decided we'll need a bigger, better, faster, nicer file system. And at the time, our original design goals stated that we should be able to allow storage and increase the storage pool. But early on, we decided that replacing Spider 1 was more cost-effective because of increased I/O requirements and increased maintenance costs on Spider. So I'm going to skip these parts real fast, but this is what a Titan Cray XK7 compute node looks like. There's the scaler and there's the GPU, and they're all nicely connected to Cray Gemini interconnect. The specs are there. The blue lanes in the middle is the Gemini high-speed interconnect. What's Titan used for? It's an open science machine. It delivers breakthrough for science for DOE, industry, and the nation. Blah, blah, blah. Let's go over. We have some early science applications on Titan, material science, combustion, climate change, etc. So these are all actually running applications and generating I/O on Titan. So coming to Spider's story, our efforts started for upgrading Spider in late 2009. It's not a sprint, it's a marathon. Actually, it's a decathlon because you have to wrangle so many things to make it happen. You have to work on so many different avenues. It really becomes a huge project. So on left, you see our completed efforts. We did some studies on understanding what actually Spider does, what we observe on Spider. Then we evaluated for last 2.5 years what are the available storage and file system technologies out there that we can use for deploying Spider 2. Then we spent quite a lot of time on writing and releasing the RFP, and then we did the evaluation of the responses. So these are all tasks done. The tasks, the red box on the right-hand side, are ongoing and pending efforts. So we are in the deployment and installation phase. So we are receiving hardware every day, and we are installing them. Next, we'll go through the acceptance, and then next, there will be the integration phase. We'll commission the file system, and then we'll roll it into production. So I'll cut these pieces short again because they were in last year's presentation. So we tried to understand Spider much better before we designed Spider 2. And we did a series of studies. We published some papers. If you are interested, you can go and check them out. And the last paper listed over there, a next generation parallel file system for the OLCF in Cray user group last year. That's a comprehensive summarization of everything we have learned so far. And the nice figure at the bottom is our design cycle as we see it. So it starts with collecting the requirements, understanding I/O demands. Then it goes into design. We architect and build a storage system, and then we validate. We roll it into operation maintenance, and then go back to the first circle, which will give us a starting point for Spider 3, hopefully. So what did we learn about Spider, the first original Spider? There's congestion problem. Thanks to Dave Dillo and his magic, we were able to avoid it up to a point, and we had 30% performance increase by just redesigning some pieces of the software without adding any hardware to the system, and that was a nice boost. You might have the term fine-grained routing. That's it. What else we learned about Spider? 42% of our I/O workload is actually reads. We were thinking that I/O is mostly write dominant, but if you look at it at the end of the day, it's like a 60-40% split that we have a heavy read activity on our file system. What else we learned from Spider? We had a substantial amount of small I/O requests. The left figure is the PDF, the right figure is the CDF of our I/O request sizes. And however you look at it, there are a bunch of small requests in our I/O mix. So, come on. Our evaluation efforts. I don't know which one is which. One of is Dave, one of is me, but I'll let you guys figure it out. But this really looks like our evaluation environments. We are creepy. So, based on our understanding of the evaluation efforts, we decided that just by running stock I/O benchmarks out there was not going to do it. So we decided we needed a new benchmark suite. So we put together a new benchmark suite, and we decided that it should be comprehensive. It should have a block I/O portion, and it should have a file systems portion. We wrote a new benchmark called FAIR-LEO. It's based around libaio libraries, and then we put wrappers around the FAIR-LEO. FAIR-LEO is a block engine that does sequential random read-writes to any block devices. So that's our block I/O benchmark. And then we took the OBD filter survey because early on we decided that Lustre will be our choice for Spider 2 as well, so we didn't have to look very far. We took the OBD filter and we put wrappers and changed the parameter set, and we came up with a new way of running OBD filter based on what we have learned from our understanding of I/O workload characterization on Spider 1. So we tuned those two. So what does the benchmark suite does? It's fully automated. You provide a list of devices, and it runs for itself for hours and days, and it kills the file system or the storage system. And then it catalogs and stores the results and plots them for you with GNU plot, so it's all ready in one place that you just look at the pretty pictures and say, yeah, it sucks. And then we released this in 2010 to public. We shared it with the public and our vendors. And so far we received positive feedback. Positive feedback being mostly like, wow, you really trashed the file system or the storage system, which we think it's a positive feedback. So we put together a storage evaluation testbed. We tried to access the storage and file system technologies before they were GA. And we tried to work with our file and storage vendors, friends, partners. Before they release their product, we tried to embed them into our, we tried to embed ourselves into their design cycles and evaluate their products, learn more about them, provide feedbacks to them, what is missing, what can be done better, etc. So, and the right-hand side is our testbed environment, really. We dissect people over there. We embed and we evaluated embedded or integrated solutions. We evaluated block solutions. We evaluated host-to-storage network solutions or host-to-compute network technologies. We, at some point, couldn't get our hands on a missing piece of technology, so we made a site visit to a friendly HPC site and learned more about the missing technology at there. So we really spent time on evaluating whatever we can get our hands on under the sun in terms of what we can use to build Spider 2. We spent like 2.5 years on this one. So after all of this, we started, it's time to write the RFP, put our requirements all together. So we started writing in fall of 2010. We gathered requirements, we started writing the document, and when we thought we were ready to release it, then unfortunately there was a flooding in Thailand, and this prices spiked up, so we had to wait until they come back down. And there was some, following that, budget sensitivity issues, so it got delayed, and we finally released our RFP in late 2012, and we started getting responses back in December 2012 as well. So, what were our requirements? We asked for 1.2 terabytes per second block level performance for sequential writes and reads. We wanted at least 1 terabyte per second cluster level aggregate performance. We asked for 240 gigabytes per second block level random write and read performance. We asked for minimum 18 petabytes of storage after rated. We asked for SAS or IBFDR hosted storage connectivity. We didn't close the door to fiber channel, but we said we'll prefer these two. We asked for parity check on read. We asked for every read operation should be checked before they were returned to the user and verify that they are reading the correct data from the disks. And we asked for performance under disk rebuilds to be a certain level, etc. So it was a lengthy document. And we got some responses. And after carefully evaluating the responses, we selected DataDirect's network proposal to use for our Spider 2 project. So after negotiation, we ended up getting the system that's spec'd out there. So we asked for two things. One, the big file system, which we dubbed as Scalable Storage System, or SSS. And we asked for a test and development system, so we can start developing tools and features and test configurations, etc., before rolling the big system into production on the TDS system, test and development system. So the technology is based on DDN's SFA12K 40 system. For the SSS, we are getting 36 of them. Each will have 562 terabyte nearline SAS disks. There will be roughly 20,000 drives in the SSSS. The after rates capacity will be 32 petabytes, and we are expecting greater than 1 terabyte per second aggregate performance. Test and development system, as I said, is a smaller replica of the SSS. It's again SFA12K. InfiniBand FDR connected all around, storage to hosts to the computes or to the other OLCF resources. It will have 282 terabyte nearline SAS drives in the TDS system. So, putting this all together, the facts about Spider 2. It will have 32 petabytes of capacity after rates. How much of that will be presented to the users after formatting is yet to be seen. We are expecting greater than 1 terabyte per second aggregate performance. We'll have 288 Lustre OSSs on the system, 8 per each 12K couplet. We'll have 4 MDSs and 2 MGSs. We will be running Lustre 2.4 all around on this system. So we might use DNE down the road. We are planning to use DNE down the road. So hence the 4 MDSs. It's configured in 4 rows. Each row has 9 12K couplets and 1 infrastructure couplet. Infrastructure rack will have all of our OSSs, top of the rack switches, Ethernet switches, etc. They will be all embedded in every row. We'll have 208 port core FDR switches to provide connectivity to other OLCF resources. We'll have 36 port FDR IB switches, which will provide connectivity directly to Titan. And there's a typo over there. We'll have 432 Lustre Titan LNet routers that will provide the connectivity between the Spider 2 file system and the Titan system. So this will be our Spider 2 architecture, roughly. There will be a Xeon scalable I/O network 2 in middle, connecting everything together. The right-hand side is the Titan Cray XK7 machine with 432 I/O routers. The left-hand side will be the OLCF 3 scalable storage system, or Spider 2. There's nothing new here. Not that anything I haven't said. Everything will be InfiniBand FDR connected. So this is a graph that shows our expected speeds and how they are fitting all together in terms of interconnect speeds, etc. There's nothing over there. So what we are delivering to users at the end of the day. This is what's important. We are a center that is missioned to enable open science for DOE and industry and nonprofits, etc. So we have to serve our scientific user base. We are not just building the fastest system, fastest computing system, or fastest file storage system because we can. We have to do something useful with that. So we are trying to make our users' work cycle, computational work cycle, much more easier to use, much more efficient. So we are trying to deliver more than 1 terabyte per second Lustre scratch space to our users. Right now, we have the first generation Spider, which, if I remember correctly, Jason can correct me, we have all around more than 350 million files on it, and it's more than 80% full. So, and it's a 5-year-old hardware sitting on the floor, so it's coming to end of its life. So we have to act fast and deliver something new to our users. So the system, as I said, will be based on Lustre 2.4, and it has why 2.4 because it's the next maintenance bridge. We want to be on that one. It includes features we want and require, like large stripe count, which is important for us to increase the shared file performance. It has distributed namespace, so we don't have to chop up a huge storage area into smaller file systems just to increase the scalability of metadata performance. We can keep it as a single namespace and chop it up into smaller MDSs instead. It has horizontal and vertical metadata performance improvements in 2.4, which we want. It has imperative recovery, which we really want to shorten our recovery time. So all of these put together, we are really pushing to get to 2.4. According to our plans, we will not be using 2.4 on, we will not be using DNE right out of the box, but we want to be able to roll into DNE down the road. Right when we start the file system, we won't enable multiple MDSs, but we will be doing that gradually down the road. So our integration efforts. Since 2.4 is a new beast, we have been doing extensive testing on Lustre 2.4. So our tests can be categorized into 2 broad classes. We do small-scale tests. James Simmons, raise your hand. He's our main Lustre tester. He's our miracle worker. So he's running around-the-clock small-scale tests. We have a single Cray XK7 cabinet, which is called Arthur, and we have some storage in our testbed that's dedicated to that one. And we have a Lustre 2.4 file system, which James tears apart and rebuilds practically daily. And he runs tests around the clock to check for stability, regression, performance analysis, etc. on the small-scale tests. So we try to do early detection of problems and bugs, and we try to correct them, send out fixes and patches upstream. And once we have sufficient confidence built in that a particular version is stable enough for large-scale tests, we roll it into our large-scale test schedule. And our large-scale test is actually running the 2.4 on the Titan scale. So we deploy it on Titan and try to see how long will it hold on Titan. We don't have high expectations. We know it will break at some point, but we want to see how long it can hold itself until it breaks down. So roughly our schedule tells us that we can do 1 large-scale test per month. We so far did 3 tests until the beginning of 2013. We are creating extensive post-mortem analysis reports on after every test. We detail what we have done, open bugs, problems, and send it out to our nice luster vendors. And with their collaboration, we get patches and fixes and etc. And we roll them into our small-scale testing and test it, and then the cycle goes back on. We did some, under our integration efforts, we also did some InfiniBand FDR testing on Cray. We found out that by using Mellanox Connect IB cards and with some tricks, we can get up to 4 gigabytes per second per Cray LNet router, so which is nice. We are trying to get that into production, push Cray and our other vendors to make that happen. So our schedule. We have all the infrastructure delivered except the long-haul cables to connect our Titan to our Spider 2 file system. Our block storage is being delivered. We'll finish the delivery in early May. We are working on releasing a luster support contract, RFP. We are looking for level 1, 2, and 3 support. So if you're interested in going after that RFP, which will come out at any days, please send an email to our purchase officer. The email is up there. Follow-up will go into block level acceptance, which we are hoping to be completed by the end of May, hopefully. We'll do the file system integration by late August, and we'll commission the file system by sometime in September. Pretty pictures. Dave. Dave is kind enough to install our DDM pieces and infrastructure pieces together. And you see the old Spider flag up top over there, which is not reflecting the reality, but it's a good nostalgia up there. So this is what it looks like, and it's coming along piece by piece, row by row. So if you have any questions, I'll field them. Sure.
A question about fine-grained routing. Is there any, are you aware of any development effort that could bring some of the performance benefits of fine-grained routing, say to customers that at a smaller scale that don't want to introduce so many LNets or additional configuration complexity? It seems like maybe there's some kind of syntax that could be added to or LNet module options, or some additional intelligence built into LNet that could make this complexity less.
I'm not aware of any other development efforts, but I will let Dave Dillow answer that question in more detail for you. He's just sitting right in front of you.
I'm completely unaware of any efforts to that end, but that would be an excellent proposal to bring to the technical working group, because that does sound like a need that could be filled.
Any other questions?
Yes. I heard you have spoken about 4 MDS, both for Spider 1 and Spider 2. Then at the end of the presentation, you were saying that you are not going to take advantage of the DNE feature of the version. So I didn't understand the reason for having multiple MDS and whether it is possible to have multiple MDS with, for example, with the version 2.1, so with one of the production version that is already available for the general public.
So we are going to use 2.4, not 2.1 to start with, and down the road we will use DNE, but not right at the very beginning. We want to play a little bit conservative over there. We'll start with a single MDS server, but when we buy hardware, we want them to be identical, so we are buying 4 of them.
Oh, so you are starting with just one MDS.
Just one MDS.
Okay.
I mean, that's the bare minimum you can do. So
Okay.
we'll start with one. And then actually, we haven't done extensive testing on DNE. So we don't know how that works. So we are trying to test out the file system, how stable it is, how scalable it is, how performant it is. Are there any regressions that will haunt us? We are testing those. DNE will be a second phase of extensive testing, and when we have sufficient confidence built in it, we will roll it into production slowly, but not right now.
Thank you.
Your 4 gigabytes per second on a client sounds really good. Was that on your small scale test, or was that end to end all the way through the LNet to a simulated client?
I will let Dave Dillow answer that one, but it was not a small scale test. It was directly measured from Cray Titan. Go ahead.
So that's not to a client. That's on a router node, which will have a lot less overhead. Clients still remain a work in progress.
On the question about the fine-grained routing, there'll be a white paper coming out from the CUG user group that talks about how Cray's given a good shove in that direction. They've kind of come up with a configuration syntax that takes a lot of that FGR into account, and some tools around doing online cable validation and LNet checking and all of that kind of fun stuff. I don't know what their plans are on releasing the software per se, but at least there's a pretty good paper on talking that forward.
There's one more from Andreas.
Yeah, so there's actually a patch that's in Garrett about route priorities that was developed at Fujitsu and is, on the cusp of landing. So I guess it would behoove us to get Nick to look at that patch because, we want to make sure that if we're adding in priorities and things and they've already done work too, that, they're going in the right direction.
Wow. All right. Sarp Oral, ladies and gentlemen. Thanks.